Hi everyone. So my name is Guillaume, and today I'm going to talk to you about IDEs and compilers and how we're trying to integrate all of them together. So I guess I don't really need to introduce Dotty much anymore since you've seen Martin's keynote. But briefly, this is this new research compiler that should become Scala free at some point, which has a redesigned type system internals, but that looks really similar in the surface. And yeah, check out the website if you want more information on all things Dotty related. But Dotty is also a chance to redesign components of a compiler. So for example, we improved incremental compilation by avoiding under-compilation in some cases. We also have better pattern matching checks. And the algorithm we implemented actually is now reused in Swift, which is pretty cool. And some of these things are also being ported back to Scala 2, like the improved incremental compilation. And of course, if we want people to use Dotty, we need to provide a good developer experience, which means we need to provide good tools. So we have a REPL, which even has syntax highlighting, like Ammonite. We have a documentation tool that is used to generate all of our documentation. And we have, of course, IDE supports. So how did we do that? So let's first start by looking at the state of the art. So the kind of IDE support you can get today in Scala. So there's two kinds really. There's the one based on the Scala presentation compiler. That is the Scala IDE based on Eclipse and Enzyme. And on the other side, you have re-implementations of the Scala type checker, and there's only one beside Dotty. It's the Scala plugin for IntelliJ. And all of this have done really good things for making it possible for people to use and be productive in Scala. But they're also kind of hard to reuse. First, because there are a lot of lines of code, and they're kind of tied either to a specific IDE or to a specific version of the Scala compiler. So when we were designing the IDE support for Dotty, we tried to come up with some design principles to follow to avoid getting into the same issues that the current IDEs have and hopefully improve the situations. So the first important one is code reuse. As much as possible, we want the IDE and the compiler to share code so that if you find bugs in the compiler and we fix them, they're also fixed in the IDE. And because testing the compiler is much easier than testing an IDE, which typically involves a lot of interactive things, it makes it much easier to get something which is robust and not get bugs which are impossible to reproduce. Second is editor agnosticity. As much as possible, we don't want to be dependent on the fate of one specific editor like Eclipse, because depending on what's trendy this year, some IDEs are going to be used more or less. So we can't expect everyone to want to use the same thing. And of course, and probably the most important one, is that it has to be easy to use and to install. So let's go through these principles one by one and see how we implemented them. So first off, code reuse. What does this mean here? It means that to do the kind of interactive features you expect from your IDE, like go to definition or renaming, as much as possible, this should be done by asking the compiler about its internal representation instead of trying to reproduce what the compiler does in a different way. This means we want to query the compiler. So really, what's a compiler? What does it do? A bunch of things. Basically, this is a list, an incomplete list of all the phases in the compiler. You start with a parser that takes your source code and gives you untyped abstract syntax trees. Then you type check them, and then everything after that is just a series of transformations that simplify the trees until you get something that you can emit as JVM bytecode or as using some other backend. If you want to query the compiler, you mostly care about the typer phase, and I'll explain why shortly. So imagine you have some source code, very simple source code. You have a final val which is called lm, its value is 1, and you have some other val foo which refers to lm. And this little flag I put here is the cursor position in your IDE. And at this point, the user wants to jump to the definition of LM. So to do that, you need to figure out the position of the definition of LM. And if you look at the tree you get after type checking, it looks a bit like this. So it's not a string anymore, it's at this point an abstract syntax tree, but if you pretty print it, it looks like this kind of code. So at every node, basically we have a type and the position of this node in the source code. And based on this, we can answer the query because the type of LM gives us enough information to find, by traversing the trees, where LM has been defined. And once we found this tree node, we can figure out its position in the source code. And then we can tell the IDE jump to this position. But if we go a little bit further in the trees produced by the compiler, say we go after constant folding, then at this point we cannot answer the user query anymore because information has been lost by constant folding. We went from LM plus 1 to just 2 as the tree. And at this point you don't know that there was a tree called LM at this point, so you can jump to the definition of LM. So it's really important for IDE support that the output of the compiler type checker preserves as much information as possible that can then be used by tools like the IDE. And then we can, of course, simplify and remove this information, but only in later phases. So to recap, to query the compiler, you want to store the trees you get right after type checking, and you can answer IDE queries by traversing these trees. But this leaves one question unanswered, is what to do about code that has already been compiled. Because typically in a project, you're going to have a few files open in your IDEs, and at every keystroke, you can ask the compiler to retype check them. But then every other file in your project, which has already been compiled, you don't want to recompile them every time you type a single keystroke, because you already have class files for them. So to explain that, I need to introduce another concept, which is pickling. So pickling is a phase in the compiler that happens a little bit later. And this phase basically takes some information from the type check trees and store this information so that it will end up in the class file at the end. So in Scala 2, this already exists, and it's used to store method signatures. Basically, if you want to support separate compilation in Scala, that means I have a.scala, b.scala, b depends on a. I first compile a, and then at some later point I decide to compile b. I need to know the signatures of all the methods in a to be able to call them. And in the JVM bytecode, we already lose some information because the JVM does not represent things like type parameters at all. So this we know the name of all the methods in the JVM bytecode, but we don't know their exact type signatures. So this needs to be stored separately, and this is stored in the pickled information in the class file in Scala 2. In Dotty, we do the exact same thing, but we go further. Instead of just storing the signatures, the API of your classes, we store the complete type check trees, and this is called Tasty. So Tasty, if you've seen the keynote of Martins, is this amazing thing that is going to solve all problems in Scala. Like gives you binary compat between Scala 2 and 3 and automatically give you JS and whatever. But here we're mostly interested in what it has to do with IDEs. But first, to basically briefly explain, the original motivation of Tasty is another attempt at solving the binary compatibility problem. The problem is that if you always use JVM bytecode, then whenever the compiler changes its encoding, say of traits in Scala 2.12 compared to Scala 2.11, then everything breaks because the encoding is different, and class files using one encoding cannot refer to class files using another encoding. And you can solve this by always compiling from sources, but then you also can break things when the type checker changes. So type inference in Scala typically evolves say someone finds some example where you want something to type to be inferred correctly, it isn't, so we change the algorithm and we hope, we test things and we hope that it doesn't break too much code. But it's always possible that some code that used to compile now doesn't compile because inference changed slightly, or because implicit search is resolving things a little bit differently. So always recompiling things from source code is also not very practical. And Tasty is kind of a middle ground between these two things, because we store the trees as they are after type checking. And type checking already takes care of all the things that move the most in the compiler and that are the trickiest to get right, which are type inference and overloading resolution, implicit search. But at the same time, it's much more high level than JVM bytecode. So when we change things like the encoding of traits, or when we decide to output Java 11 class files instead of Java 8, that doesn't influence what's stored in the Tasty trees. So how does this relate to IDEs? Well, basically, we only care about Tasty for IDEs because they contain the type check trees. And as I explained previously, using the type check trees, you have all the information you need to be able to query the compiler to do things like go to definition or find our references or renaming. So this is very interesting because it means that we have one data structure we use to query the compiler, which are trees. And this works at the same time for trees in the open files in your IDEs and for all the trees in your class path that have been compiled using Dotty. So based on that, we made a set of very simple interactive APIs to basically query trees and do lifecycle management of a compiler. And we can use that both in the IDE and the REPL. Again, code reuse, yay. So when you ask for completions in one or the other, we're going to use the same code. And in the future, we'll probably enhance that by adding APIs for dealing with interruption handling or partial type checking. Because when you're in your IDE, basically every time you press a keystroke, we currently type check the whole file, but we could do things in a better way and only type check the section of the file that changed. And we could stop the type checking as soon as you decide to add another keystroke. And the interesting thing about all of this is that it's less than 1,000 lines of code. So it's pretty easy to maintain compared to a full-blown implementation of the type checker. On to the second principle, editor agnosticity. So there's this IDE portability problem, which is if you have a bunch of IDEs and a bunch of programming languages, you need to multiply the number of IDEs by the number of programming languages to get the number of plugins you need to support all of these things properly. And that's bad because it means a lot of duplicated work in development effort, since for each IDE you're going to have to redo a plugin. It also means that to write the plugin, you need to be an expert in both how the IDE works and how your programming language compiler works. And usually people who are expert in one are not expert in the other. So how do we fix that? Well, you might also have heard of that in a previous talk, but there's this thing called the language server protocol. And the idea is, instead of tightly coupling an IDE and a compiler, you can instead make a protocol so that IDEs and compilers can talk to each other. So on one side, you have a tool, which is usually your compiler, your IDE, sorry, and on the other side, you have a language server, which is usually your compiler. And when a user does something like opening a document, you're going to tell the compiler, hey, the user opened this document. And every time something changes, you let the compiler knows. And then on the other side, the compiler can send information back to the tool about, say, error messages and more complex things. So basically, the way it works, this protocol was first implemented in VS Code, but has now been implemented in a bunch of other IDEs too. It's based on JSON RPC, which is a simple protocol for sending messages back and forth using JSON. And you start with the IDE notifying the language server anytime there's some user action like pressing go to definition. The language server has to maintain some internal representation of all the code, so it knows what it means when the user press go to definition. And it's also responsible for telling the IDEs about warnings and errors. And the IDE can send requests. Usually that's the user which is triggering the request, like say I want to rename this thing to some other thing. And it's completely asynchronous and cancelable, which means that anything that can happen can be stopped, and that the UI of the IDE does not have to freeze every time the compiler is trying to type check something, because it doesn't have to wait for a response from the protocol to continue working. So how do we implement a language server for Dotty? Well, it's pretty easy because all the low-level handling can already be handled using the LSP4j library, which was implemented for Eclipse, but that we can reuse. And all the interaction with the compiler can be done using the interactive APIs we discussed in the previous sections, which means that in the end, it's only a few hundred lines of code to implement the language server. And just to show that there's basically no trick to it, I can show you how the definition method works. So this is responsible for doing go to definition. Every time the user press go to definition, we're going to have this method called, and our only job as the language server is to implement it. So as input, we get the parameters, which are just the position of the cursor when the user asks to go to definition. And the way it works in LSP4j is that you return a completable future, which takes some token for cancellation that you can use to check if the user interrupted the request. But that's not super important. So you get both URI for the document, which tells you which file the user pressed go to definition in, and a position. And based on these two things, you can figure out which compiler to use for this particular document. Because usually in a big project, you're going to have multiple sub-compilers, because you're going to have, say, a source project and a test project. They're going to have different class paths. So you need to know which compiler to use to get the right class path. Once you do that, we can just query trees using the interactive APIs I talked about earlier to get the symbol that corresponds to the position the user is at. And then we can, based on that, get the tree where this symbol is defined, so the tree of a class, and then traverse this tree to find where the definition of the symbol is. And then we just have to do some mapping that back to something the LSP4j API understands. All right, so last design principle, how do we make this easy to use? And the way it works right now is we have the Dotty SBT plugin that you have to use anyway to use Dotty. Also is responsible for IDE integration. And its job is just to look at your SBT build, find all your Dotty projects, compile these projects, generate configuration files based on this project, install the VS Code extension, and then launch VS Code. So what kind of configuration files do we generate? So there's basically two things. First, when VS Code is started, it has no idea which version of Dotty you're using, how to start the language server. So we just give it the name of the artifact on Maven, and then we use Coursier to fetch this thing. And once the language server has started, it needs to know all your sub-projects and all their class path. So we have a JSON file which say for all your projects which compiler version you're using, what flags to pass to the compiler, which directories are used by this project, what's the class path of all your dependencies, and where the output of this project resides. And So this works pretty well, but the main issue is that we have to generate these files, and every time you change something in your build, you have to regenerate these files. So that's why we tell people to start VS Code using SBT and not the other way around, because that way we can be sure that these files are up to date. But that's not really practical. So what we really want is some way to query the build tool to get all this information at runtime, instead of having to have a compiler a plugin for the build tool to get this information. And yesterday there was a talk on the build server protocol that is trying to solve this problem, among others. And just to recap, basically the idea is, instead of having to make plugins for build tools to extract information, we can just ask them. The same way we have a language server protocol to ask the compiler, hey, how do I go to definition? We should have a build server protocol to ask the build tool, hey, what's the list of projects that compile with Dotty, and what compiler flags do they have, and what class path do they have? And once we have this thing, it's even better than using plugins, because it means that it should work for any build tool that implements the protocol and not just SBT. And there's one other missing piece of the puzzle, which is some kind of discovery protocol, because basically the end goal is that the user experience is just you start your IDE, whatever IDE it is, and if you install on your IDE marketplace the plugin for Scala, and then it automatically figures out everything, which means it needs to figure out how to start the build server for this project. So there needs to be some kind of discovery protocol, which doesn't exist yet. Probably some kind of file in your project that says this is the command line to start the build server protocol. Alright, so to recap, here's our design principles and how we achieve them. So we achieve code reuse by implementing APIs for interactive usage, which are not specific to any IDE or any specific tool, and can be already used both by the IDE and the REPL. We achieve editor agnosticity by implementing the LSP, and we achieved ease of use using an SBT plugin that basically reduces everything to one command. But we can do better. We can do 0 command, hopefully. To go further, there's one other missing piece of the puzzle, which is, well, how do you debug stuff? And if you followed the trend so far, you can probably guess what's going to happen. There's a debug server protocol. So the JVM has a very complete API for debugging called JDI, the Java Debugging Interface. And that's how all debuggers for Java are implemented. And we're in luck, because there's already a Java debug server that implements the debug protocol. So as Dotty compiles to Java bytecode, we can just reuse that, and most things just work. I haven't actually merged this in Dotty yet. But there's one thing which is non-trivial to implement, and that's expression evaluation. So imagine you're in your debugger trying to debug some really simple code. Here we have a class with 2 methods, and you put a breakpoint here. So now the flag means breakpoint. And now you want to execute foo, because you're in debugger, and in debugger you're used to being able to evaluate expression. But how do you do that? Because foo takes some implicit parameter, and we are not in the compiler here, we're just in our debugger, and somehow we have to tell the debugger how to run this foo thing. So that's not trivial. And the first thing we can do is just, well, okay, let's try just to run the compiler. So if we run the compiler, at the end of the compiler pipeline, basically foo has been replaced by this.foo of y, because implicits have been resolved. But then what do you do with this? It's some code in some method somewhere. So based on the position of this thing, we can add a phase to the compiler, which is only used for expression evaluation in the debugger, and that phase is going to extract the code that you want to evaluate in your debugger into a static method. So why is this useful? Because once you have a static method, if you can compile it to some class file and run this class file on the JVM, you can just say call this method to your debugger. So of course things are a bit more complicated than that, because here our static method takes parameters which correspond to things which were local variables on the stack when you called foo. But you don't have this information directly when you're in the debugger, so you need to mangle things a bit, because the only information you're going to get from the debugger is you have a self, which is the current class you're in the debugger, and you have a list of local variables, which we can represent as a map from the name of a local variable at runtime and its value. Alright, so we're on the debugging VM. So there's two VMs here. There's the debugged VM, which is the one running your program, and the debugging VM, which is the one where you type your expression that you want to evaluate and send to the VM, which is currently stopped at your breakpoint. So on the debugging VM, we can run the compiler, we can compile global to some class file, and then we can load it in the debugged VM. And once we've managed to do that, then we just need to call global.exec with the right arguments. So to do that, we're going to cheat a bit and add a magic method in the standard library that we can use to execute some random class file on some random class path, which is just going to look for this class file and call the exec method. Once we do that, on the debugging VM, basically all we have to do is find the class path for the global class we just created, find ourself and our list of local variables, and then do a remote call that sends to the remote VM and tells it call this method with these parameters. And this is pretty horrible to do because the JDI API is really low level, but it's possible to do. And just to prove that it actually works, so this is VS Code running on Dotty itself. So we're using our compiler to compile our compiler, and now we're going to use our compiler to debug our compiler. Whoop. Okay, so here's some test case. We have some object with a val of type any, and its right hand side is 42. And we're kind of curious of how does this get compiled, because any gets erased to object, but 42 is an int, and int is not an object. And if you look into this, you'll probably find that there's something called boxing that the compiler does, where it's going to wrap your int into a Java long integer. And to understand how this works, we can put a breakpoint. Here's a breakpoint on box, and then run it. To run it, we use the debugger interface of VS Code, where we've set things up using the launch.json file, which basically tells you, I want to run this main class. In this project, the project name gives you the class path using all these arguments. All right. So I press F5, that starts the debugger. Can maybe. Alright, so the debugger stopped, and already we get a lot of things for free just thanks to the Java debug server implementation. We get a list of local variables, and we can go inside these local variables to get the fields inside all these things. We have a call stack, and we can even like hover over things, and if they're on the list of local variables, we can see inside them. Alright, cool. Now here's where it gets interesting. So I can send expression from my debugging VM to the debugged VM. So if I just send 3, I get back the value of 3. And here we are doing a pattern matching on 3.tp.widen. So I can try to find the value of that thing and print it. Yes, so its value is this thing, type ref of this type of type ref, somewhere in this various int. So if you're not used to how the compiler works, that's not very enlightening. But thankfully there's something called show, which basically pretty prints this back to what you'd see as a user in error messages or in source code. But show takes an implicit context argument. But since I'm lazy, I don't want to pass the implicit context by hand. So I want to let the compiler do that. Okay, so I think the output is wrong here. But basically, what's happening usually is things work out, and the show method ends up being able to figure out that it has to take this context here because it's in your list of local variables, and magically you get back the properly pre-printed value. And of course we can step over variables and see at every point how things work. All right, let's get back to presentation. Ooh, okay, so this all seems cool, but are there any catch? And yes, the major catch is in some cases the things which are in scope when you compile your code do not match exactly the things which are in scope when you run your code. And the main point where this happens is when you have an inner method in some method, and you try to call a parameter of the outer method. And the way inner methods are compiled in Scala is they get promoted to just methods of a class, but they'll take extra arguments which correspond to the arguments inside the class that you use inside the inner method. And the issue with this is that if you have an inner method that does not use some parameter from the outer method because you don't need it, and then you're in the debugger inside the inner method and you try to use one of these parameters, it's just not going to be accessible, because when that method was promoted to a method of a class, we didn't pass it the parameters that it did not need. And we could change that in the compiler, but that's not something you want to do by default, because if you capture too much things in your inner method, then you might leak things if you store this in a closure that is then sent to stored somewhere else. But other than that, most things should work. So future work. Basically, we want to do some optimizations. Like I said, right now, every time you press a keystroke in your IDE, we're going to recompile everything in the current file. We could try to do less of that and just recompile things that have changed. And we want more features, of course, like documentation and hover, because documentation is important to show to users, of course. And we can't do that yet because Tasty does not store documentation information, but we're working on changing that. And once we do that, we'll get other things for free, like the possibility to do to do incremental generation of the documentation, because instead of starting from source files and generating documentation, we could start from tasty and generate documentation. And we'd also make it very easy to display the documentation inside the REPL, for example. And of course, better build-to integration using, hopefully, the build server protocol. So to conclude, I think it's important to have interactivity in mind when designing a compiler, because there's lots of little things that matter. For example, when you're in an IDE, you're going to, most of the time, the code you're going to write is not going to compile or even type check, because there's going to be syntax errors. But you still want things that go to definition to work more or less reliably, which means you need your parser to be tolerant to errors and recover from these errors. And when you store things, your trees, like in the tasty format, you also need to think about interactivity, because if you want features like renaming to work, you need to store positions of all your tree nodes very precisely. Otherwise, your renaming is not going to be able to figure out which part of the code needs to be renamed how. You also need to design your build tool with interactive use cases in mind. Otherwise, you end up in situations where, like we have right now in the Scala ecosystem, where it's really hard and everyone has to reinvent basically plugins for all the build tools they want to support to be able to use them in IDEs. And hopefully we can get interactivity to go beyond what IDEs and REPLs currently have in Scala, which is mostly limited by having to solve the same basic problems a lot over and over again. And hopefully we can avoid that now that we have building blocks like the language server protocol that take care of the low-level details for us. And I think one good source of inspiration is the work done in IDRIS. So there's this whole book by Edwin Brady called Type-Driven Development with IDRIS, which gives, I think, some good hints on the kind of things we could do if we focused more on improving the user experience of IDEs. Thank you very much. I'll open to questions.
Yeah. Thank you very much, Guillaume. Do you have any questions? Yeah.
Where the language server will live in the end? So will it be a part of compiler or part of SBT or some standalone process that will somehow integrate with SBT?
So the language server right now in Dotty is a separate sub-project which lives in the Git repository of the compiler and depends on the compiler. I think it's going to stay that way. And the main question is, well, how do you get this thing? And the way it should work is basically in your favorite IDE, you install the plugin for Scala, and then the plugin itself finds and resolves the compiler from Maven using, for example, Coursier to fetch the jar and all its dependencies and start it.
But in this situation, how will, for example, SBT console and IDE coexist? They need to talk to the same server somehow, right?
So the SBT itself does not really need to talk to the language server because, well, SBT is or your build tool is the source of truth for how to compile things. And then both the language server and other users like SBT console are going to ask the source of truth, like, what's the class path for this thing? So that's what the build server protocol is about. And the language server has to query the build tool about, well, how do I compile this thing? And then the build tool is responsible for making sure that if you have at the same time some console running or some other compilation running and the IDE asks for a compilation, things work out and you don't get conflicts or you don't get everything to freeze.
Okay. Any more questions now? No? Then thank you very much again, Guillaume.
Thanks.